a few people who have actually pronounced epidemiology right. Every time I'm introduced, they destroy that word. So I'll be walking around, but I know that I've got a microphone. I'm happy to project a little bit more, but I think this would be good. Today is going to be very hands-on, so I've provided a collab notebook for you that runs, and that you're going to be writing some code in there as well. I have to make sure I remove some of the solutions, but I hope I did. Anyway, even if not, you can kind of see how things are done. We're going to start off with very basic things, just to make sure that we're kind of at the same level, talking about what PyTorch does under the hood and how it could actually does similar calculations as NumPy does. But by the end, we're going to quickly ramp up. So we start off with like basic PyTorch commands. We'll do like a linear regression on there, and then we'll talk about transfer learning, doing your own computer vision models, and then if we have time, which I believe we should, we'll actually go into style transfer, which is a little bit of fun. All of the code here is executable. You don't need to modify anything, but one of the nice things about it is that you can upload your own images and do things that you would want to do as well, to make it a little more personal to you. That said, my style is very free-form. I'll be chatting, I'll be walking around, but if you have a question, feel free to interrupt me at any time, and then we can actually just answer it on the fly. That's kind of like the way I prefer to go things. I think there's a couple of people who have just walked in, just to be reminding everybody, this website here will take you to this collab notebook here. All right, so show of hands, how many of you have actually coded in PyTorch before? That's 1, 2, 3, 4. Okay, perfect. This is the right amount of audience that we have. This is meant to be an introduction to it. We're not talking about more complex things in PyTorch. This is just meant to be a tutorial on how to actually start working in PyTorch. Sorry, I have a tendency to do that. And I'm just going to take this off, because I can project my voice. You guys hear me well?
Yeah.
All right, good. This is a little weird to hear myself in an echo.
Sorry.
Yep.
I think if you don't wear the mic, it's not going to pick up on the camera.
Oh, good. Darn it. All right, so sorry, I'm going to have to hear myself, and once in a while we're going to have to hear a little bit of banging on the microphone. Yeah. It's very, very, very true. I'm going to try to put it to a spot where it's. There we go. Better? Cool. All right, stop picking me up. All right, so I forgot what I was saying, but we're going to start with some very fun things in PyTorch. I know that there was about 4 or 5 of you here who would raise your hands saying that they worked with PyTorch before. One of the first things we need to do is first connect to our runtime. So it should already automatically be connected to a GPU, but if you go to runtime here on the tab, click where it says change runtime type, you should see GPU connected. If it is not, select GPU. We're not going to be working with TPUs just because the graphics card underneath, like under the hood, is actually a GPU. Then we can just connect to it, or you can do that by actually running the very first line of code. So we're going to start off with just kind of the simple stuff, the usual suspects. Here's the stuff that we really care about. This section right here, this is where we import PyTorch, so we're actually going to import Torch, but we can also do some aliasing as well. So this is their neural net package, this is their autograd or their gradient descent, like backward differentiation. So this is what we're going to be using for our neural networks. We can define custom functions here. We've got data sets and data loaders that we're going to be using for our connection. So if you're trying to get to this Colab notebook, it's right there. Yeah. And then we've got some Torch vision stuff, things for the computer vision models that we're going to be running. And then this Torch summary is actually quite a nice little synopsis that tells you actually how big your model is and how much memory it should take up and how many parameters you have, how many of those are trainable. It's a nice little thing in there. The rest is just things that you should have seen before, and if not, I'm happy to explain anything there. So we'll run the very first line. This is just going to import all of our files. Now, if you did this correctly, this should say device type CUDA when I run this line. So if I'm just going to hit device, and you should see device type CUDA index 00. So CUDA is basically the equivalent of the x86 architecture for GPUs. So you'll see references to CUDA a lot. That is the same as using an Intel x86 architecture. Right? It's just now on the GPU side. Everything we're going to need for today's tutorial is all in this download path. So we're just going to run this line, and you'll see that this is going to populate our left-hand side with a whole bunch of new files. But you feel free to look through them. There's just pictures and images and things for the conference. But it takes it a second. And then you'll see the left-hand side will populate with all of the things that we're going to be running. Once in a while, or as you guys have been familiar with Colab, you'll get disconnected from your runtime after a certain amount of inactivity. Just rerun the first couple of lines here, and then go straight to whatever section we're in at the very top of that section, and then you'll be fine. So the sections are meant to be sort of modular, so that you don't have to worry about running the entire code to get to where you're at. They're pretty modular there. All right. So sections here, basically we got kind of PyTorch, just neural nets, image recognition and transfer learning, and then CNNs from scratch, and then the supervised learning transfer nets. And if you get disconnected and we're in the neural net stuff, you would just go click here and run those lines from there. You don't have to worry about running this stuff all of it. All right. We're all good. We've all got our code running. You should see now a couple of different files on there: data, captions, and list, and models. All good? Cool. Okay. There is a larger version of this PyTorch tutorial, so this is the abridged version. At the end of the class, I'm happy to send you the one that has a little bit more stuff. It's got some stuff on natural language processing and not chatbots per se, but something similar. Okay. So one of the first things we need to talk about when we talk about PyTorch is what is a tensor, because we may all be familiar with an image. Well, an image is a tensor. So if you think of Grumpy Cat here, when we look at it on our screen, it looks like one 2D image, but really it's comprised of 3 different matrices. Those 3 matrices stacked across each other. Again, it's good to that image, but so a matrix is a 2D tensor, a color image is a 3D tensor. And basically you can think of tensors as the generalization of matrices. And you can have, for example, a movie would be a 4D tensor because you've got images that change in time, so that gives you that extra dimension. So what you see here is that they tell you how each much of these, for example, for an RGB image, it tells you how much of the image is activated in the red spectrum, the green spectrum, and the blue spectrum, and then that sort of kind of overlaid on top of each other, giving us the image that you like. Is this fine on the screen? Oh, yeah, that's pretty good. So here's kind of some, these are all tensors, right? And I use that word very, very generally here. So you've got a vector, this is a 1D tensor. You've got a matrix, a 2D tensor. Here is that image of Grumpy Cat that we saw there. That is a 3D tensor. Here's an image of a 5D tensor, 4D tensor, and then here's a 5D tensor, which could be a series of movies, right? That would be and obviously you can generalize this to how many dimensions you want, but the kind of analogy breaks down pretty quickly after 5Ds. And I don't know many applications where you need more than 5D tensors. Now, very similar to NumPy, tensors have a type. So you can do torch.float32, which would be a float tensor. So there are you'll always see 2 different versions of it. So you'll see this column here and that column there. The very first column, or the CPU tensor, is what happens when you're not connected to a GPU. You can still use PyTorch on compute. PyTorch on compute will just give you a float tensor. If you were on the GPU, you'll have torch.cuda, whatever that thing is. So this is pretty important because there are going to be times where you're going to want to run your model on a CPU for quick inference, but when for training, you might want to do it on a float, so you got to make sure that you're actually keeping track of the correct data types. Now, one of the very first things that we need to do here is actually to see kind of how it works, right? So we've already connected to our runtime. We should already be connected here, so we can actually create random tensors just like we can in NumPy. So this is going to be a very good parallel to like why PyTorch is so important is because it allows us to do NumPy-like calculations on a GPU. So there's a lot of parallels because of it. So if we run here, we could actually create our NumPy array, and here's our torch random array. So you'll notice that it always tends to start with the tensor at the very, very top here. You notice that the NumPy array does not. This is a good giveaway that you're on PyTorch, and so is the D-type. Note here that this says float.64, not torch.scuda.64, because I did not need to push this to the device yet. You actually have to transfer things to the GPU, as you'll see later on. For now, don't worry about that part yet. But we could actually even check their D-types. Right, so we've got a torch tensor, we've got a NumPy array. So ND array here is the equivalent of a tensor. So an ND array can be 1D, 2D, 3D, 4D, 5D, and it is the exact same equivalent as a tensor. They just call it ND arrays instead of using the more formal mathematical word of tensor, which you do not need to memorize. So we can create 3D tensors in a very similar way, exactly like NumPy. When you do a 2D tensor, it's the number of rows and the number of columns. In a 3D tensor, it's the number of matrices, the number of rows, and the number of columns. So it kind of feels a little weird. So you're going to see 3 4x5 matrices instead of 5 3x4 matrices, which is what most people think of when they do that. I know I did, and then was like, what's going on? All right, now we can change the D-type pretty easily. We can create things like, so torch.zeros, as you could imagine. This is the same thing as np.zeros. It actually gives you a matrix just or a tensor, for lack of a word, full of zeros, and then it's going to have that specific D-type. So you can actually change D-types on the fly. You can change D-types after the fact. You can change D-types upon instantiation. So here's a float, where instead of, it's still zeros, but you notice a decimal point here, letting me know that this is 0.0. And it does automatic typecasting, so it casts to whatever is the more agreeable one. So if you've got basically a long tensor, or for lack of a better word, an int tensor, they call it here long. If I add it to a float tensor, it casts the long as a float so that I can actually make that operation happen, even though these are also zeros. But you'll just notice that the decimal point here makes it everything a long tensor. Sorry, float.
So you're saying it always upcasts it, or it goes to whatever is first, or what?
I totally forget. It's whatever one allows for the operation to not lose any efficiency. So if you've got, yeah. I always forget if it's up or down. I just know that it does the right one. All right, where was I? So, yep. We can also create explicit tensors. So this would be a tensor of 1 row, 2 columns, 2 by 3, or well, 2, 3. And here we could also basically say, like, I can create a specific matrix and then obviously create its type. So here's the tensor, here's its type. And there's also a couple of things here that are a little bit novel for PyTorch. This is this method applied to a tensor that is a new _ones. And what that does is that it says, tell me whatever type X is, create a new matrix or a new tensor of all ones of explicitly this size. But it inherits the D type of X, right? Which is, I think, something that is not typically seen in NumPy. So you see here now I've got a float.tensor. I noticed that I didn't have to explicitly call it here. X was a float tensor, but my Y here is automatically a float tensor. There's a size method, just like in NumPy. And we can add tensors in the usual way. Obviously, when you're adding tensors, they have to be the same size. So there's several methods for adding tensors, and you'll see why this is a little bit more useful as we get into actual training models. This is just a very simplistic version of it. So we can actually take our two tensors, we can x and y it, we add them together. There's also a torch.add method where I put in the parameters. So I'm saying I'm going to torch.add x comma y. And then another one, which is the .add underscore method. So I'm saying to y, add x. The underscore in any of these methods means do it in place, very much like pandas, like transformations with in place gets true. So if I do y.add, notice here that this is the value. Y originally was supposed to be all ones, so when I come here and I click on y actually gets changed in place. It saves a little bit of writing, but it's very, very common to see it in PyTorch, in PyTorch code when you're training things. Slicing and indexing works just the exact same way as you would in Python. So this is going to be the third row, second column, and on. Remember, as you all, this is the Python conference, you know that Python's are indexed, so I don't really need to harp on that. And we can reshape things as well. Here's the tensor that I'm describing. So I'm going to basically create random tensor of 4x4. I'm going to change it with this dot view. This dot view still exists and still still works. Never mind. And I can say x.view16 basically give me back one tensor of all the size 16, or I can do x.view of -1, 8, which means gives me exactly 8 columns back, as many rows as I need. And then they actually finally added reshape as a method that you can call. Because before there was no reshape method in PyTorch, so code that would seem to look like it would work would not. But here you'll actually see all three of those sizes. So we've got the original size of 4x4, then I cast it to a 1D vector. Here, then I change it to a matrix, and then matrix is the same size, but basically the same thing with the -1. So the -1 says give me as many columns as I need, as long as the number that follows is divisible by the total cycle. So if I had put a 7 here, this would not work. Now, we can convert to and from PyTorch and NumPy. So we can get, say, here's my A, so this is torch.ones. And then if I want to change, if I want to convert to NumPy, there is an a.numpy method here. So I can just say, well, give me B. And if you notice here, this went from being saying tensor here to now saying array. So this is no longer the same type. Now, this is always a fun one to ask because I get many different answers. What do we expect for result A to be? So I'm going to add A, and I'm going to add 1 to it, and I'm going to do it in place, and then I'm going to print A, and I'm going to print B. What do I expect the result for B to be? These are not, this one's a NumPy array, one's a PyTorch tensor. You can cheat by place run, but just curious, what do you all think? Is B going to be the same as A, or is it going to be different from A? They are the same. B is a pointer to a.numpy. It is not a pointer to, it's not a new place in memory. If I wanted to do .copy, then it would be different. But unfortunately, fortunately or fortunately, like you have to understand what's happening in the hood here when you change between NumPy and PyTorch. You may want to, if you want to do transformations to it outside of it, that doesn't want to, that won't interfere with the actual tensor itself. Make sure that you use the copy method because it is a pointer to a.numpy. It is not a specific point in memory with the value 1 in it. So this is a very common, confusing thing in Python.
Is that because the tensor is just wrapping in NumPy already, and it's just giving you the pointer to the internal implementation?
If I understood correctly, so basically B is a pointer to A, and then it says call a.numpy.
Right, but I mean, if it's basically giving you back the same thing as a.numpy, just giving you back a reference to NumPy array that's already inside the tensor.
I believe what you're saying is true. I'm not sure what the very, very last part, but like, generally I think the gist of it is true.
Tensor is just wrapping NumPy array, so if you've got NumPy, just giving you the direct reference.
I think they're different D types. So PyTorch is a kind of its own thing. You can call methods to put things to NumPy, and vice versa. You can put things to Torch. But I think they're, in memory, they live at different networks. But generally, I think that the gist of what you're saying is still true though. Right, we can convert from NumPy to PyTorch. So obviously we saw that there's a .numpy method to convert to NumPy. We can convert from NumPy to Torch pretty easily. Saying Torch from NumPy is a little bit different of a call, but same thing. You'll always notice here that the tensors don't give you as many decimal points as the NumPy array. That's just for printing. Nothing. They literally are the same margin underneath, even if it doesn't show the same number of decimals. All right. Any questions thus far? Trust me, we'll speed this up very quickly. This will get a lot harder. But I do want to talk about a little bit about why PyTorch is, well, and this is not just true of PyTorch, by the way, this is true of TensorFlow. It's the autograd, so automatic gradient descent, so that this actually does all those derivatives for you behind the scenes. And this is one of the reasons why it's so pretty cool. So if I'm going to do this mathematical operation, and I'll actually show you the math behind it as well. If you do not understand calculus, do not worry about it. It's just to let you know that what we expect to happen does happen behind the scenes, and all of it is done with one command. So we're going to create a tensor here of just number ones everywhere, and I'm just going to do some operations to it. So I'm going to have my x, my independent variable. Here's my dependent variable y. It's going to depend on x. This is very similar to how you're going through a neural net, where you're actually, for every layer of the neural net, you're being passed to some function. So you are the independent variable if you're on the very far left of the neural net. You're definitely a dependent variable or a complex value, a dependent variable, as you're going through that neural net. So imagine this is the very first thing we do in that neural net. We do 3x plus 7. So we do that, all good. It's going to give us the same result that we expect, all 10. So then, because we created, by the way, this requires grad true is only needed for this example. Typically, when we're working with neural nets, this is automatically happening behind the scenes. You don't need this. This is just for this toy example here. So because y was created as a result of an operation, it now has a gradient function method. So this gradient function method is an add backward method. This could actually be multiplication or sinusoidal, whatever actual mathematical operation you called on it. And this is actually what's tracking that automatic derivative behind the scenes there for you. Now I'm going to do more stuff to it. I'm going to say, well, now z is 2y squared. And then I'm going to take the mean of z, right, and see what those values are. You'll see that we basically get 200 because the mean of all of these four values is also 200. Now, we're going to do this by hand, right? So if I were to take this derivative by hand, we could actually just do the chain rule from calculus 1. 1/4 of z gives us, I think this is supposed to be 1/4 here. Oh, no, the 2. The 2y squared cancels it out. So 1/2 3x plus 7, we take that derivative, we apply it at x equals 1, we get 30 back. Now, for us, all I need to do is do w dot backward. So it says take this thing here and go backward through all of its operations as you're doing backward gradient descent or backward propagation through a neural net. And you notice here that I get 30, which is exactly the number there. So this means that we don't have to worry about tracking the derivative of things in a very convoluted neural net, right? With possibly hundreds of layers or thousands of connections. It's pretty straightforward to just do that and know that it's all being tracked behind the scenes, with the exception of you defining a custom function. So if you're doing, for example, physics-derived or physics-derived like machine learning models, where you need to have a function that models some sort of physical phenomenon, then you would actually need whatever that derivative is, but you can actually do that later. That's a step that's done through PyTorch that you can say here would be the backward method. All right, so now let's actually work on a real piece of an example of this actually going through this all together. So this is going to mimic a lot of what we're going to be seeing in a neural net model. So we're going to start with a linear regression example, something that I think we should hopefully all be familiar with, especially for those who work in machine learning or are enthusiasts in machine learning. So we're gonna have 1,000 points here. What we're gonna do is we're gonna create a bunch of random numbers, and then I'm gonna give it a bias, right? So we're an offset here. And then I want to be able to fit this data as close as possible using my PyTorch method, right? So if we were to be doing this in sklearn or SMS, the OLS stats model, we can do this very simply, but this is showing you that whatever we can do in there, we can also do in PyTorch. So what we're going to do is saying, well, what does this data look like, and how do we fit this data? So I'm going to be, here's my model. I'm basically going to try to, so what I'm trying to do is, I'm trying to mimic 2x plus 3 here. So this is this, sorry, 3x plus 2. Yeah, so 3 times these values plus 2 times this values is going to be the data that I have. That data is going to be randomly generated, so it's going to be noisy. And then I'm going to try to find line of best fit through it. So here is my thing. For those that don't know, at is the equivalent of matrix multiplication. In PyTorch, you can do torch.matmul, M-A-T-M-U-L, but it was so much easier to write an at than it. All right. Now, here's what our data looks like. So this is all my noisy data. Clearly, there's a trend going upward. What I'm trying to define is then what is the line that best goes through this data while minimizing the error, which is exactly what we're trying to do in a neural net. We've got a optimization function. We're trying to minimize its error, and we're going to do so via backward descent. So I need to define what my my optimization function is here. For linear regression, we're going to use the mean squared error. And all that is just basically trying to minimize the difference between my predicted value and my real value squared and take the mean of it. Right, so very simple mathematical operation here. Now, I need to give it some sort of initialization. So whenever we start training a neural net model, we need to instantiate the weights, because the weights are going to be randomly defined, but we need to define those ahead of time. I'm going to basically say my guess, or my very first thing I'm going to do is to say I'm going to guess -1, 1 instead of 3, 2, right? Because obviously we don't know what the answer is for 3, 2. Oh, sorry. Need to define A first. Now I could actually show you what would happen in that very first model. So that very first instantiation, basically saying this was my guess, this class is clearly not that. How do we then optimize what we're trying to do here so that we can get the best model? So again, this is just the thing that I need to do because this is a toy example, but it helps you illuminate what's happening behind the scenes here. I actually need to create a parameter. This is a neural net parameter, meaning that this is a weight that I need to update. They call them parameters, right? So when we talk about, when we see it in the summary, and when we start looking at computer vision models, it'll ask you, it'll say, like, how many parameters does this model have? It's talking about weights. So now, if you notice, thank you. It says, here's my tensor, requires graduates true. This is now letting me know that I can track backward gradient descent off of here. And now, here is my actual training step. I'm gonna come in, my y hat, so my predicted value of y, is gonna be my x times my current value for my guess, right? So my current parameter for a. Then I need to calculate its loss. Okay. Then I'm just doing some printing here, don't worry about that. Then I'm doing loss stack backward. This loss stack backward we said was exactly how we do backward gradient descent. It's literally one line of code, perfect. One line of code, we don't need to do anything else. Then we need to change the values of the weight. So we do that with torch.noGradient. So that means do not change any values. So you'll actually see this throughout the code when we get to the computer vision model. So I'm trying to give you like a sweet synopsis of it here. And we're saying, do not upgrade any of these weights. So now go, give me my a.guess, subtract, and remember the underscore means in place, my learning rate times the gradient of that function. This is this canonical formula for updating weights. Sometimes you'll see it with a plus sign. Sometimes you'll see it with a minus sign. It just then changes whatever the value of that learning rate is. So I'm doing it here with the subtraction. And then I need to zero out that gradient because I don't want it to be informed by a previous step in my training when I'm already in a new spot in my sort of optimization well, trying to find the lowest spot. I don't want to be informed by something that happened after I had updated it already. So you will always have to zero out your gradients. And you'll see that when we get, and I'll call it out when we see it in the computer vision model. So here is our function. Now, here's my learning rate, I define it as 0.1, and then I'm just gonna go through this thing 100 times. And you'll see that it prints every 10. Okay, and you see that we kind of are stabilizing around here of around an error of 0.11, doesn't seem to be getting any better, perfectly fine. And then I'm gonna do the parameter here. You notice here that I need this detached thing. This is just so that I can plot it. So this is just one of those things where I need it for this. Wow. We now use PyTorch to do linear regression. Seems a little bit overkill, but you'd be surprised at how much linear regression can actually work. Now, so one of the things that I'm going to do very quickly is like, yep, I put it here. I didn't want it to be here. I'm going to just get this off. I know that you all have it. Just remove it and then try to do it again without it. So the exercises for you all is because solving linear regression, or basically the method of least squares, is a closed formula, meaning that there is a defined formula for it to solve method of least squares. These are all of our tensors defined in our data. So the exercise for you was to actually go in here, delete that line that I had accidentally left for you all. I want you to write up the theta and see how that compares to your actual guess. Right? So we're going to compare our theta with our A dot guess, and I'll give you guys like roughly 5 minutes. I'm happy to answer any questions. Here is the formula, and here are two ways that you can do an inverse and the transpose. Those are the two things you'll need, and then however else you want to go about it. You can do it in one line, or you can separate your parentheses and the next one, and then do those all separately. But this can be done as one line of code. And just kind of give me a thumbs up if you've got it. You got a question? Oh, you got it? All right. It's still the same thing. Oh, y is not a scalar. Oh, y is a vector. That's an arrow. All right. So for those who got it, how much does your value differ pretty close to the actual optimal source. Yeah. There. So if we wanted to code this all in one go, we'll have data is equal to torch t of x at x inverse. Yeah. Mine's a little bit different. You might have different values, but there you go. You can do it in one actor. So this kind of gives you a little bit of knowledge of like the inner workings of every single piece, like how we can, well, maybe not this much so, but there are going to be times where you need to multiply matrices together or tensors together, so you can use the add method. But we're sort of now going to be shifting our gears into what the neural nets are, right? So how many of you are actually familiar or have worked with neural nets in the past, even if it has to do with PyTorch? All right, so good half of you. Cool. So I'll maybe go through this a little bit more quickly, but this is just kind of level setting on everyone, like what is a neural net, and we'll start off with sort of the linear perceptron, which is the very first thing. This is kind of like mimicking how a neuron works. So if you think of like a neuron in your brain, it takes an input, it takes all, it synthesizes that input, and it gives you some sort of output. Now, one of the funny things here is that this is linear regression. This is a mx plus b, if you were to do it in the algebra sense. So basically what it's saying is it's doing a linear position of all of these different inputs and just multiplying it by a weight, but it's just taking their sum. So it's just basically doing the linear regression of all of those values. So the superposition, sorry, not superposition, the sum of all of those values there. So, now here, when we think about one sort of neuron, this is kind of like the model that you'll see, but we don't have one neuron, we've got many, and what we're trying to find out is how does this then scale and what are the implications of it are. So we can actually do that in, sorry, I meant to say linear compilation. Well, I'll get back to this in a second. I'll actually jump here to the regular neural net. So what we're looking at here is that, well, that model that we saw before was literally just one perceptron. So we'd have these weights go to this one input, and then it'll do some linear combination of those values and give you some sort of output. Now what we're doing here is saying, well, there's more than just this one place where it needs to connect to. These data are being fed to actually a whole bunch of different points in the array, or in this case, our neural network. So every single one of these data points actually connects to each one of these. Whether those weights are 0 or not is dependent on the model. So what are the things that you're trying to confirm? So ultimately, what we're trying to do is take in our input and give some predicted output back in the case of classification models. So in this case, we have binary classification. We're trying to find out, well, what's the likelihood that you're this class, and what's the likelihood that you're that class. And we're going to be doing that via a very convoluted neural net. So for each one of these, we need to then say, well, how does this input data affect the very first layer? Then how does the first layer then impact the second layer, again with weights. So you're going to see a whole bunch of indices here. And ultimately what we're trying to do is be able to separate our classes very much like we see here. So if we have here is our sort of our activation function. So we're going to go through all this whole neural net. At each point in our neural net, we have a nonlinear function that is actually activating it. And it's going to help us split this apart. So if we were to have this be our A1 and this be our A2, in this case, we would be able to separate that data pretty easily. This could also be done visually. But if it wasn't for the fact that this activation function is nonlinear, literally all we would get back is lines. Because if you were to go through and work the math of every single one of those weights hitting every single input, if there's no nonlinear activation, it is all linear combinations of those values. You would just do a whole very nasty algebra equation where you would have one variable and a bunch of coefficients that affect it, and those would all get added up. So if without nonlinear activation, all this would give us back is lines. So it is the fact that the nonlinear activation function is what makes neural nets what they actually, the magic that they can do. There's a paper written many years ago talking about how a deep enough neural net with enough data can accurately mimic any mathematical function. Any. So obviously, depending on that function, depending on that thing that you're trying to mimic, it may require more data, more compute than we actually have resources for. But we do know that this actually can mimic any mathematical function. So this is why neural nets tend to be used so frequently. So for every single one of these points in that neural net that I showed you earlier, I should probably just script down there too. What we're going to be doing is we're going to compute the alpha value. So we're going to go through that whole linear, we're going to go through the forward propagation of that neural net. So we're going to start at the very far left with our input values. We're going to go to every single layer, multiply by our weights, do our nonlinear activation function, go all the way to the end, and then can say, well, did I predict the class correctly? Yes or no. How off am I? So calculate the error in the true value versus the predicted value, and then update those weights. That updating of the weights here is my new weight should be my old weight plus the change in gradient. I remember before I showed you I had subtraction. Doesn't matter which one you do, it's just changing the sign. And I don't actually need this part right here because I can do the a.add underscore and it does it in place to it as well. So in a more general sense, right, here when we're talking about loss functions, we could typically do like a mean squared error loss, but here we actually want to define that loss to be whatever it is that we need it to be, whether it's a cross entropy loss, etc. And then what you're trying to do is find the point where the gradient of that loss is 0 or as close to 0 as you can get. So that's where the minimum of your model is realized, and then that's what we hopefully outputting. And then we then go through here with some learning rate parameter here, so that the previous equation didn't have a learning rate parameter, but here is just a learning rate so that you're not oscillating around the actual minimum. You're actually trying to get there in a way that you can do it so pretty easily or nicely. So now let's run through a linear equation model. So we're going to run through our first very neural net here. This is going to be the most complicated adding machine you've ever seen before. This is what I call my Rube Goldberg adding machine. So what we're going to do is we're going to take a model. We're going to say this is a sequential linear neural net. It's going to have 2 inputs, 1 output. Bias equals false here means don't give it a bias layer. It would just give you 0 anyway when you finally update it. For my optimizer, I'm going to use my autumn optimizer. It is a more robust version of stochastic gradient descent. You can read all about it in the documentation. And then for criterion here is going to be mean squared error loss. Right? So that's the loss we're going to use. We'll actually use different ones as we work through our examples today. And then I'm just going to print the model. So what does this actually look like? So nothing fancy. This will actually start getting bigger and bigger as we go through this. So we're going to have a linear model. It's got 2 input features, 1 output feature that bias is false. That's my model. That's all I have. Now what I'm going to do is in this step here is, well, keep track of the total loss. I'm going to iterate through this 10,000 times. And then very first one is a progress bar. I need to do my data preparation. This sometimes happens outside of the actual loop or depending on what the model is that you're running. So I need to tell it, well, first generate random numbers uniformly on 0 to 4. That's what I'm doing there. And then it says, well, my data is my variable and my target is the sum of those two. So I'm taking 2 numbers and I'm outputting their sum. And what I would like to see is how long does it take for my neural net to actually determine what the output is. Now, we as humans should be able to do this very quickly. 4-year-olds can do this depending on the size of the data and how smart they are. So we're going to feed forward this through our model. So we're going to take our output, we're going to put our data through our model. That's going to give us our output. Our loss is going to be our criterion. So that's our mean squared error loss. Our output versus our target. We're going to, well, this is just the loss for tracking things. We're going to do our backpropagation. So we're going to 0 out our gradient. We're going to do loss dot backward. And then this optimizer dot step does the updating of the weights for you. So this is the entire code for backpropagation that you'll write, which is why it's so nice. So let's go through this. Should be very, very quick. There we go. Let's plot this. So, all right, before you guys plot, how many steps do we think it'll take the computer to learn 1 + 1 = 2? Like 1,000 steps, 4,000 steps? We did all the way up to 10,000. So this is just like there's no right answer here. This is literally just one of those things. It had to see 2,000 examples for it to finally understand that 2 + 2 is 4. So this is what I mean by they're very great if you've got compute resources, but this is why they take so long to train sometimes. It does take a while for it to do even something as basic as adding 2 numbers together and determining what their sum should be, right? I do not need to show a 4-year-old 2,000 examples, but I do need to show this data set, this neural net, which was very simple, by the way. It was not anything fancy. Now here, I'm just kind of showing you like what that would look like. So in a typical case, this is where you have your training data. This is where we don't have training data. You can think of it as like, okay, does this fit well with our validation set? But obviously, I give it a continuous block chunk and not anything outside of there. So, but you'll actually see what happens as we work through it some more. So this is the kind of the diagram that I talked about. So for each of those steps, it's basically saying, take my input, progress through here, do my nonlinear activations, check the result. Is this, like, how good is the result of the prediction versus the real one? And then do the backward propagation, updating every single one of those weights that you see connected here by lines. All of those weights need to get updated. And then I go through it again. So I do this step many, 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 many times. Right? So this phi here is that activation function. So when you're going through here, you're basically doing the sum of all of the weights times the inputs, the respective input of the data. This should look like mx plus b. This is linear combination, but this phi here is what allows it to be nonlinear. And most of the time, we use things like sigmoid functions or ReLUs. These are kind of the very common ones that you'll see. This is likely the most common one you'll be using, but there are several different methods here that you can see here. All right, so for here now, actually what I'm going to do is I'm going to take that exact same model, the same approach that we took before, is that instead of having a linear model, so I'm going to have my nn.linear. So this sequential means that do all these steps in sequence. And then I say, okay, my very first input is 2 values. My output is 20, so it goes from 2 to 20 different lines, or different perceptrons, then 20 to 20. But for every single one of those steps, I'm doing a sigmoid activation function. So it tells you here all the 7 layers, or all the 7 steps in there. And then this is the exact same code that I wrote before, but instead we're going to use a different model, not the one that we wrote before. So this one is going to be our model with nonlinear activation. Takes it a little bit lower because it just has to go through all those places and update all those weights. And when I run this one here, I still actually needed it to run a little bit longer, right? So before we were actually getting pretty close around 2,000. This took a little bit longer, but if you notice here, it's because it was trying to do some nonlinear activation function. So it was trying to start curving out as you're going through it instead of finding the right thing. So as you notice here, what this sigmoid activation function, or in this case, our nonlinear activation function, it's letting do things that are outside of this line. So if I didn't have a nonlinear activation function, I would predict this line perfectly like we saw before. This nonlinear activation function is allowing me to do things outside where I may have validation data or things that I'm trying to do that are just generally intrinsically nonlinear. I'll skip this one because it's the same thing but with the revenue. Now, when we typically train neural nets, we want to do several different versions of it. We don't always want to just like run it once and say, okay, we found a minimum, because we have the problem of local minima versus global minima. And so what we would typically do is say, if I had actually started, say, up here on this red one, and that was my very first time I ran this model, I may actually end up in this well here. This well is a local minimum, not a global minimum, but the model won't see anything otherwise. So it'll be like, oh, your model has reached, its optimum point. It's going to stop training. It's going to do a validation. It's going to tell you, here's your performance. But if I train several of these models at once with different instantiations or different randomizations of the weights, I may actually find this one, which is the global optimum. So this is a very common thing that you might usually do. You're running it on different instantiations of those weights. All right. So now onto the more fun stuff. So the image recognition and transfer learning. So I've shown you kind of like a general schematic of what a linear neural net looks like, and that's very similar. That's very typical for a neural net that doesn't have convolutions. But whenever we're looking at images, we need to train the model in a way that it actually understands things about the geometry of it. So for example, that wheels are round. That humans have faces that look like this in ours. That's got eyes. So what we do is actually, well, in a convolutional neural net, we actually scan that image. So we don't take in the entire image at once. We actually scan chunks of that image. And this little patch here is meant to be mimicking that. So it's basically going to be scanning this image and then kind of taking information off of it and updating those weights and saying, like, does this have a corner, et cetera? And I'm generalizing here. I'm going to show you kind of like how this actually plays out. But the convolution is basically saying, like, give me the inputs of this, and it's going to multiply it times the inputs of a convolution. Those inputs of that convolution are going to be updated as you're training through the model. But it's trying to scan these images for shapes and things that will help it recognize what that is. Now, that's what the convolution does, this pooling, or what's called max pooling. You can think of it as a way to zoom in on an image and look at things in different levels of scale, right? So if I'm trying to do several things in this image, so I'm trying to recognize the fact that there's a car there and also maybe a bird there, the car is going to be taking up a lot more of that foreground versus that bird's going to be small, so that max pooling helps me zoom into areas where I can then identify those other images. Now, it does this in many, many different steps. Ultimately, you get to the last layer, which is going to be a flattened layer, so you basically go from a tensor that is in some given shape to a vector. Then you're going to do a fully connected layer. This fully connected layer is going to look very similar to that neural net that we showed the schematic of before. And then we're going to do some sort of activation function and get our predicted classes. Now, we don't need to reinvent the wheel every single time we do a computer vision model. One of the things that we can do is that we can leverage transfer learning. And transfer learning is very useful because whenever you're working with images of things in the real world, meaning you're trying to identify, I don't know, Superman versus Batman, whatever it is that you're trying to do here. If those things are things that have been modeled in other models, for example, like Google's ImageNet, you can actually take some of those parameters because it takes a very long time for those parameters to actually optimize. So this is no longer true. And now you can train ImageNet a lot faster. But ImageNet took 14 days to train. 14 days continuously around the clock, compute. I know that analogy no longer holds true today. We can actually do it in a couple hours now. But we don't need to do it in a couple hours. We don't have to. And so this is actually from a paper that is linked at the very bottom, that as you go through each of the layers, so what each convolution does is it basically tells you, like the very first convolutional layer will identify lines. So like, is there a line like this and there's a line like that. The second layer will then start identifying lines touching, so triangles. And the third layer, et cetera, will do more and more, so you'll actually get more complex shapes. So this layer 3 is really deep into it. But this layer 3, if you notice, these honeycomb patterns are actually being identified in this actual real images. These are human faces. We've got ladybugs and things that are generally red in shape. So the tomato, we'll leave this with car. Here are wheels, so it starts to identify things that are around. So it basically says, they actually have images for almost all the layers, which is actually really cool. I only showed layer 3 here, but it's basically showing you, like, in each layer, what section is getting highlighted by that image. So here, this layer 3 is like helping you identify shapes. So if you have similar things in your training data, you do not need to start from scratch. You can actually leverage all of this material. So this is what transfer learning does. What transfer learning does, it says, here is the base model, right? So here is all of the information about shapes, what a frog looks like, what a ladybug looks like, what a car looks like. And then it's drilling it in a way that will help identify the 1,000 classes that were in ImageNet. Now, for your task, or whatever task that is, you may not have 1,000 classes. You may have 2. But you know that your images contain information already contained in here. So I don't need to train this part by myself. I'm going to say, give me all the weights from this model, and then change this last little bit for your specific purposes. Yeah?
So is it possible in advance to predict which layer will identify which feature, or is that a black box?
Black box. I think it's model dependent. Like, if you change the architecture of the model, that layer that identifies something will change.
Okay.
So that's why it's not always like layer 3 will do this. Layer 3 in ImageNet did that, but layer 3 in VGG, they do.
Before they trained ImageNet, do you think they would, accurately say, like, we think layer X will identify?
I don't think so. I think it's done like after the fact, post pre-train. Or yeah, out of story, sorry. So what we're going to do, and you all will have the data in here. So I've given this talk at PyData Miami before, and I actually am from Miami. So we're going to detect, or we're going to use images of Cuban sandwiches and arepas, which you can all find here in Manhattan. There's also a very big Cuban and Venezuelan population as well. So these are the king and queen of the Miami food scene. So we have a whole bunch of images in one of these folders that has images that I scraped from the internet of Cuban sandwiches and stuff that I found. And we're going to see if we can train a computer vision model to do just that, to identify the difference between those two. So I'm going to run this here just very quickly so that we don't run out of, so that my compute doesn't stop. But I will talk about this. So this normalized thing here, this very, very first line, this is the average and standard deviation of every single channel, or of the 3 channels, of all the images in ImageNet. Right? So when we're downloading this data set that already exists, we're going to normalize to that so that we fit that model a little bit nicer. So you'll typically see this in computer vision tutorials. They'll be like, oh, we're going to train using ResNet. And then they'll use that because that data set has already been trained. We know exactly what those values are. So those are the normalization values. These do not come from out of thin air. They come from the data set that is in the original model we're transferring from. So now, this dictionary here is our data transforms. So for our training set, so here's one of the challenges with transfer learning, that when we're typically doing it on models that are much, much smaller than the original ImageNet or ResNet or whatever it was. So I think they had millions of images for all of the different classes. So you had like 100,000 images of bicycles, 100,000 images of whatever else is there. We've got 300 images of Cuban sandwiches and 300 images of Cubanos. That's not a lot. And this is very true when you're doing typically like small scale computer vision.
So if you're trying to retrain for this specialized set of images, I don't get why you want to normalize to the overall.
Because if you don't do it, it'll be fine. Like I've run it without that line to see it doesn't really change a lot. But it's basically helping standardize the images. So it's because the parameters are optimized for that translation. So the original trained model was already normalized with those. So all of the images in the original ImageNet were shifted and then trained on.
Oh, I see.
So the parameters are optimized to those parameters,
That's shit.
to that shift. So one of the challenges of having small amount of data for a computer vision model is that it doesn't handle variety very well. So if for example, I have a friend of mine who did a model on trying to identify women's shoes. And all the shoes were pointing to the right. Like there was always just like, it was like an image of a shoe. There was not even a human wearing it. It was just an image of a shoe, but every shoe was pointing right. And then as soon as you give it an image of a shoe pointing left, it goes, I'm ready what this is. So what we need to do is we actually need to do those variety. This is our way for us to augment our data. This is literally what we're doing here. We're doing data augmentation. So we're taking in our transform, so we're taking our data, we're gonna resize it to be 224 by 224, which is the size of the original images. We're gonna put it to the tensor. We're gonna normalize it based off of those transforms. We're gonna do a random affine, so that's basically looking at it like a top-down, kind of like an angle view. And we're gonna do random horizontal flips. So that means that an arepa that is left to right should look like one that is right to left. Right? There's nothing there. We can do vertical flips. I don't think it's necessary, but there are a bunch of these transformations that you can do. You can add lighting, you can darken images, you can do a lot. But you always have to be careful of what it is that that image is doing. Like for example, do I want to detect a cat that is upside down as a cat, or do I want that to be something different? Right? Do I want that to say like, give me this as a flag or something like this? Is not something that I should be seeing naturally in the wild. So that's for you to do and decide which transformations you need. So I do the horizontal flip and an affine transformation just to give you like an angular view. And then for the validation set, you never want to touch that. There's no point in augmenting your validation data set. You're only wanting to augment your training data set. So then here's where those data sets lie. Here's where the validation data sets lie. And then here is where we're actually going to be loading the data. So this is just our data loaders. We're going to do a batch size of 32. We're going to shuffle. That means that every time it adjusts them in, it's going to shuffle those around so that it's not doing it always in the same order. Because you can basically give information to your model that will take it harder if all the images always in an EBA and then always a human image. So then, there we go. Here is the fun stuff. So we're going to take our model. So from models with an S, .resonant50. So models with an S comes from the PyTorch package. It's going to have our resonant50. This pre-train gets true is what's needed. This to device. This is now we're finally going to be putting things on the GPU. And this line right here. So for param in model.parameters, param requires grad gets false. That's me saying do not update these weights. Because I am literally transferring all of those parameters over, and I don't want to change those. What I do want to do is modify the fully connected layer. This you'll actually need to check into the documentation of like, what is that final layer called? Sometimes it's .fc, sometimes it's fully connected. Whatever it is, you need to look at what that model parameter was. So for resonant50, it's model.fc. And I'm saying, change that one out to be 2048 to 1000, which is what it was before. And I'm saying, take it from the original 2048, now give me 128 extra ones, do this review activation, in place gets true, sounds very similar to what you would need for pandas, and then you say, okay, then from that 128, give me my two options out, right? Give me my, whether you think it's an arepa or whether you think it's a Cuban sandwich. Here is our cross-entropy loss. That's how we're actually defining this, and our model optimizer is still going to be our model atom. And here is that summary that I told you about. So you have to give it an input size, so like what does my image look like? So my image is 3 channels by 224 by 224. And if you notice here are all the parameters involved in every single one of these. So this is how many weights it would have. So total parameters of resonant50 is about roughly 24 million, of which we're only training 262,000. The other 23.5 million are frozen. We are keeping the original values they had in resonant50. This is what the transfer part of it is, because we're doing non-trainable stuff with trainable stuff. That model is about 300 megabytes in size, almost 400 megabytes in size, there we go. And what we've got here, we're going to train our model. So I'll try to talk to this a little bit. So the very first part is just printing stuff. So you need to actually look at your model in two different phases. Your model is going to have a training phase and a validation phase for every single batch that you do, or epoch. So if the phase is training, set my model to train. This means this model.train means my weights are now allowed to be changed. If my model is not in train, it's in validation, I do model.eval. This model.eval freezes all weights because you don't want your model to be training on validation set and actually updating those weights because you're not supposed to be updating those weights when you're looking at validation data. So this model.eval freezes all weights. So you'll always typically see this, just running loss. We're gonna have our inputs and our labels from our data loaders. We're gonna put them to the device. We're gonna run this on the GPU. Our outputs are gonna be our model inputs. Our loss is gonna be this. So this is, again, two very simple lines of code. And then if we're in the training phase, do the backward descent. So we're gonna do our loss step backward, well, zero our gradient, do the backward descent, and optimize our steps to basically update all the weights. And then this is just additional stuff for tracking your errors. I don't know if I ran this, I don't think so. Yeah. All right, we're gonna run this very quickly. I only do three epochs here. So remember, I had roughly 50-50, I had roughly 300 of each. So if my model were to be guessing randomly, it would get 50% of them right, 50% of them wrong. So when we first do our first epoch, we get an accuracy of about, and this is on validation, by the way, get an accuracy of about 78%. Our validation is also for us to split 50-50, to the point where after 3 training rounds, or 3 epochs, we're starting to see some really weird things happening here. Our validation, our loss accuracy is a little bit higher than our validation accuracy. Validation accuracy seems to be frozen there, but we could obviously train this a little bit more. So we have just ran our very first transfer learning model. We can save that model, check those weights. We can save it here as our checkpoint. You can save the weight by itself, or you can save the whole PyTorch model. Obviously, one's going to be bigger than the other. So you can do the state dictionary, and then here's where those weights get updated. And then we can also load from a previously trained model, if that's what you want to do. So I've actually trained this to be a little bit longer. So I'm going to do the same thing. I have to define my architecture. Before I can load in a model, I have to have the architecture be the same. So I do the resident 50. I don't need to download the pre-trained weights because I'm going to give it weights. And then I need to change the fully connected layer. And now I'm going to do model.load state dict. And then here are those weights that I need to do. And then model.eval, so I don't want to train this. This will always print out the model for you. And then, so here are some test images that we saw, and we want to see how well we're performing on them. So these are all in our validation set. And we're basically going to be passing it through and saying, like, predict what these are. The softmax is going to give me the percentage of the probability that it thinks it is one of each of those classes. And then lastly, I'm going to show this. So here are 4 images in our training set. And let's see how we performed. This is an arepa. It identified this as 66% likelihood of being an arepa, so great. This is a Cuban sandwich, 92% likelihood. This actually says the word Cuban, but it's not learning that, it's learning all of this stuff. So this is 78% chance of being a Cuban sandwich. And this one's a little bit harder. This is almost 50-50. This is 52%, 48%. This is an arepa, but I can see how it can get confused as a Cuban sandwich.
Would it be hard to add another model to understand the word Cuban sandwich on there?
If my images had a lot of text on it, then I could probably train things to like identify text. But like out of all of the things that I had, I think there was out of the 600 images, I think there were 4 had text.
I mean, you have to like train it to understand.
You need transfer learning from an OCR.
Yeah.
Yeah.
That's kind of what I imagine. Yeah, like another transfer.
We could do something, yeah, but I would say that for this purpose, it's not necessary. But if you'd be surprised at how well vision models work. So So that's kind of like the primer on transfer learning. So like if you had images that you wanted to download, by the way, there's a way for you to like Google images, and then there's a little code that you would write in JavaScript that would download all of those images for you. That's what I ended up doing. I forgot what that JavaScript code was, but you can easily search for it. Like download all images from Google Image Search, JavaScript. Gives you a little snippet. You type in your thing. You go to the console, like you go to the inspect on Chrome, type in that JavaScript, and download them all for you. That's what I did. I think it stops at like 300, which is why I have to get. But it's a good way for you to think about like things that you're wanting to identify and just play with it. You've got the entire architecture here. You just have to point into the folder where it has your training set and your validation set, and however many classes you want. I chose 2. It could have been 10. It doesn't matter. If you want to identify, I don't know, all the Power Rangers, you can give 1 class for each. So now we are 20 minutes left, and we've got 2 paths that we can go, and I want you to choose which path we go. Do we stay more on like the CNN side and start actually building convolutional neural nets from scratch? Or do we move a little bit more on the artistic side and we actually talk about style transfer and how that works and actually work on our own style transfer images? Style transfer would look like, if you're not sure what that word means, like that. Here is an image, here is a piece of art. How do I get my original image to be in that style?
From scratch.
From scratch? Well, let's take a vote of hands. I see that you're the one who voted thus far. From scratch? 1, 2, 3, 4. Style transfer. Style transfer wins. And by the way, you have the code for both. So, so there's nothing here that would be at a loss. And I'm happy to stay and answer any questions that you might have on the specific things. But this is actually one of my favorite things. That it kind of feels like now with DALL-E and Stable Diffusion that this is no longer necessary, but this was a step in order to get us there. So as the gentleman was asking earlier, like how do you know which layer helps identify certain things? You do know it after the fact. So there is a paper here by Gaddis et al. That was looking at BGG19 as a way to identify like which of these layers is helping identify physical features. So things like, is this a tire? Is this something, ladybug, etc. Versus what of this is the artistic or the style of the image. So they did very similar things that we saw in the previous one, where you actually see like how it gets activated in each of the layers. So they're saying that these 3, convolution 1, 1, 2, and 2, 1. I hope I don't get this wrong. I believe these 3 are the physical ones. This is the style one. Or if I got it wrong, it's just reverse those. But so what they're actually doing is something a little bit different because there is no right answer. So when we were looking at typical CNNs, where we looked at arepas versus Cuban sandwiches, or we looked at Resonant 50 with all 1,000 images, like there was a right answer. There is no right answer here. This is why it's called semi-supervised. You're looking at outputs and you're saying like, this is good enough, but there is no true optimization minimum. You're just going to get to a point where you say, I'm happy with the result, and you stop. So what we're going to be able to do here is, well, I always forget the name of this artist here, but obviously Van Gogh Starry Night, Edward Munch's Scream, and whoever that guy is. We can go through here and create our own images to be in a specific style. So the BGG19, we're actually not going to care about its output layers. We're going to download the model, but unlike we did before, where we froze weights and we like changed the fully connected layer, we're going to download the model and look at only specific layers and see how actually that all works out. So when we look at the BGG19, which we're going to be downloading in just a second, there are going to be the features, which contains all the convolution and pooling layers, and then the classifier, which contains the 3 fully connected layers at the end. We don't need the fully connected layers at the end because we're not trying to identify anything. So what we're going to do is we're going to get the features portion of it. So we're going to get our models, BGG19. We do want the weights. Yeah, we do want the weights. I'll put the features there. And then we're going to freeze those weights for some of the other ones. We're only going to change certain models, certain parameters. We're going to move this over to the device. So this is going to be running on the GPU now. This would probably take about 10 times longer if it was running on a CPU, just an FYI. So if you don't have, if you wanted to run this on your laptop and you don't have a GPU, get ready to wait, or you can just use Google Colab. So here we're going to load in our images. So this is just how I like loading an image. It's just nothing fancy going on here. This is still the same trained on the same data set, which is why the normalization values are the same. All right, so here is going to be my image that I want for my content and my style. So by the way, I believe I gave you the option to put in a URL. Yep. So wait. So the two images that I have, these are in my data folder. This is a picture of my dog. There's a picture of a Day of the Dead style painting. If you wanted to use a very different thing altogether, and you wanted to go to Google Images and type in Picasso, and go to his artwork, and say something, I don't know, I'm going to pick someone that I find a little bit easier. Rene Magritte. So there's a very nice one here that I like to use sometimes. Where is it? The painting at the beach. Yeah, you can use something like this. Like, you can use something like this that has oceans in the background, have things in the foreground that look like snakes, candles, etc. You can just right-click on here, hit copy image address, and put that into that function that we defined earlier. So instead of putting in this path here, you would put in, well, it's actually the picture of my dog. If you want to do it for the style, you would put in that URL there. If you have a picture on your laptop that you want to use for yourself or your pet, kid, etc., change that one there. Just upload it. Literally take your picture and drag it to this pane. It'll automatically upload. All right. So now onto the fun stuff, the actual technical bits. So we're going to put this layer out. So here we're going to actually, so you notice there's actually a lot of steps on here. So we need to identify from that original schematic that we showed, like which are the actual layers that are going to need to be modified and the ones that we actually need to capture specifically. So that's how we would find it. We would need to go in here and find exactly which one we need, but they're already marked for you, 1, 6, 11, 20, 13, 29. So this is the value 1, 1, 2, 2, 3, 1, 4, 1, 3, 2, and 5. So here's the one that does the content representation, all the rest is style. So I was wrong when I said the first three were content. So I always forget which one had what. This is the content stuff, this is the style. Yeah?
So how exactly do you?
This is from the paper.
Okay.
So this is not something that I had to go into the paper and say like which are the ones that they actually got.
And did they explain how they determined it, or was it basically they just looked at it after?
They did. I don't recall. I was trying to just recreate it without getting too into the weeds. All right. So one of the first things here is this gram matrix. This gram matrix is actually helps determine whether two things are in the same style. So for us, it's very easy to determine when two pictures are off by literally looking at a pixel-to-pixel difference. Right? If we can do a pixel-to-pixel difference, we know if these images are off. It's very different for style. How do you know one thing is in the same style as the other? There is a mathematical object called a Gramian matrix that kind of does this, although it was defined for something different before. It does work in this scenario. And what it's basically doing is it's taking that matrix and like multiplying, reshaper, so we're getting each of the features out to understand if we're calculating that gram matrix, where it is our basically doing the matrix times itself, its transpose, right? And it's doing so in a way to then determine whether or not that gram matrix has the same style of the original, right? So we're going to be doing this, comparing it to the original versus the target image, right? So we're trying to say like, how far is this gram matrix from the gram matrix of the style that we're looking for? And that's how we're going to be comparing whether we're getting closer to that style, while also keeping two different things. We're going to be keeping track of the style, but we also need to make sure that our pixels aren't changing in a way that our cat still looks like a cat, a dog still looks like a dog. And you'll actually see that in a bit when I actually go through the example here. I'm actually going to start pressing playthrough here so you actually see some of the, I'm going to explain it in just a second, but I do want to start running this model so that by the time I'm done explaining, you actually can see some outputs. So where were they? So we need to get our content features. So we defined these functions already. So we've got our content features. We're going to get our content. We're going to get our style features. Here are going to be our style grams. Right? We're going to do that gram matrix for our style features for each of those. And we need to create this clone. So we're going to be making a copy of our image and saying, where are we right now? How does this compare to the original target and to the original style? And then we need to actually be updating our losses and our weights. So this is actually the part that is much more of an art than a science. So each of these tell you how much to adjust the style. So the very, very first layer is going to be things in the foreground. So the things in the foreground, how big of an impact do you want it to have on the image? Then you can think of these as like things receding into the background. So if you think of Rene Magritte, foreground is the snakes with the candles. Background is the ocean. So how much of those do we want to play a role in it? So this is going to be very much a trial and error sort of thing. I chose these once. I think I modified them like another time, and I have never changed them since. And then lastly, what we need to do is then have a competition between this content weight and the style weight. So this is the alpha beta. So in the actual paper, you'll see this ratio is what matters. And that's how you're going to be updating the loss itself. So we're going to content the loss. This, by the way, is the difference between pixels. So we want to make sure that to ensure that this gets minimized is that the pixel shapes really aren't changing. So when we see a corner, that corner is always still there. If there is plenty of white space, then that's a space that, since all of those pixels are always going to look the same, it doesn't matter if it's local or as you scroll through an image, you're going to see that there are going to be edges that form. Those edges still have to stay there. Things that are part of a background have a lot more space to then be filled in by our artistic layers. All right, training steps. There's not a lot here difference. This is just kind of like the style weights and doing the gram matrix and all that. But here again, all we need to do is these three things for our optimization. And I am going to start at the very top. So this is the very, very first image after starting, not the original image. If you notice, I'll try to zoom in here. Notice all the swirlies here? This white space is now going to be filled in by things that are not, that can be filled in by style, meaning that since it's a white canvas or a canvas with not a lot of pixel changes in terms of coloring, then that's where we're going to start filling in a lot of those cool images. This ear here forms a border. I can fill in inside the ear. I can fill out outside the ear. That border should always be there. You'll start to notice that there's actually being painted on her head. There are things that it's never going to change. You'll always see this lamp. You will always see this painting of the Native American in the background. This carpet where she's laying on, very similar to white space, is going to start filling in with some of those features of the art style. But things like the nails are going to always stay the same because they form hard boundaries between changes in layers.
The question is, so the boundary in the ear, is that because of the way that the layers are higher for boundaries?
Correct. We want to make sure that the content stays the same.
Okay.
In the content, it's like shape versus texture.
Correct. So as I scroll through here, I'm going to go through this a little bit quicker. You start to see that there's more things being filled in, and you'll see a lot of those patterns start popping out more. And if anyone is running this on a different image or image of your own, that'd be really, really cool to see. It's always fun to see how much this is starting to get filled in here now with the roses. We'll actually show the original and the original artwork as well, and you'll see where it takes its influence from. Oh, it's still right. Great. That was just 8 images out of 20. You can run this for as long as you want. I'm going to stop it. Stop. Do I have the save one? Darn it, no. I think I do have the save. No. No, darn it. I think I should have let it run all the way to the end. I'll do it just for. Anyway, you'll see that the image of the dog gets filled in with a lot of the artistic elements of the Day of the Dead, and then the ultimately the final one is going to be different. Let me see if I have it right here in my data. Oh yeah. This is after 50,000 steps. So this is what my dog looks like now with the Day of the Dead, and I'm going to show you what that original Day of the Dead looked like over here. So you'll see where my dog takes inspiration from this. The roses that are in her ear. So you'll start to see things that might pop out for you. These earrings here really look nicely on her nails. These bits here, I think, come from generally this area here and like all the features in the white space here. So, yeah, so this is fun. I know that it's kind of feels a little obsolete now that Dolly came out. But still kind of cool that you can still do this with PyTorch. So yeah, I'm actually happy to stay a little bit after and answer any questions you all may have, but I believe that's kind of where I was going to leave it for today's presentation.